Okay, so now today we are going to discuss the outline of a compiler, what are the different steps or stages of compilation. So, broadly, there are 5 different stages of compilation. The first is called lexical analysis, the second is called parsing, the third is called semantic analysis, which includes identifying types, scopes, and checking them. The fourth stage is optimization, and the fifth stage is code generation or translation. And we're going to discuss each of them in more detail. So I'm going to explain these different stages by using an analogy to understanding a natural language. Now, lexical analysis is kind of similar to recognizing words or tokens in compiler lingo. So just think about it. Let's say there is this sentence called computing requires energy. Now when we read this sentence, this sentence has lots of characters in it, CO and so on, and then there's a space, then REQ and so on. The moment we look at it, the first thing we do is we separate these characters into words, right? And so for example, if I just write the sentence a little bit differently, it would be much harder to read, isn't it? So for example, in this red ink, I have written the same sentence, but put the delimiters, word delimiters differently. It makes much less sense. So a compiler is kind of similar. It takes an input, a stream of characters. The first thing it does is it recognizes words or tokens in compiler technical language. So in other words, a lexical analyzer is supposed to take in a stream of characters and it outputs a stream of tokens, where each token is formed by one or more characters, right? So it basically groups characters. All right. So let's take an example of a programming language. So here is a programming sentence or a statement. If foo is less than equal to 2, then bar brackets, so it's a function call, else x equals 5 semicolon. Now this string of characters looks like looks like a program, and we can kind of identify in this the words that make sense, right? So if, then, and else, these are words or tokens, and these are the tokens which are kind of special tokens of the class keywords. All right. So even within tokens, we will basically categorize tokens and say that these tokens are meant to represent keywords, and other tokens are meant to represent identifiers, and so on. And so if, then, and else are programming language keywords, which means they have a special meaning inside the programming language. Okay. Then we identify identifiers. All right. So the identifiers are basically tokens that represent variable names, function names, etc. In this case, foo, bar, x look like identifiers. Constants. So constants in this case are formed by strings of digits. So 2 and 5, or they could have been longer strings of digits like 20 or 53 or something like that. And then operators. So less than equal to, the function call operator, left bracket, parentheses, and right parenthesis. The assignment operator, right? So we can see 3 different operators. Notice that some operators are formed by a single character, while other operators could be formed by more than one characters. All right, and this is actually true for all different types of token classes. And then there is the semicolon, or which in this case forms a delimiter, right? So delimiters are basically telling you, separating one statement, one programming statement from the other. All right. So what is lexical analysis, or lexing for short? It takes as input a stream of characters and generates as output a stream of tokens. So essentially it generates tokens from characters. All right. Now let's look at parsing. Well, parsing can be thought of as diagramming sentences as trees. So for example, if there's a sentence like fast computers are more energy efficient. So recall that the first step in trying to parse the sentence would be to lex it, all right? So which means identifying tokens from the stream of characters. But once we are done with that, we would want to understand the structure of the sentence, right? And in this case, in the English language, what we are going to do is we are going to say that, okay, where is the verb? So in this case, are is the verb. And so we can see that this verb is describing what the noun on the left does, right? A characteristic of the noun on the left. So we can think of it as though it's a tree. It's we can represent the structure of the sentence as a tree, and on the left hand side of the tree, so the root of the tree is the verb on which the entire sentence hinges, and on the left hand side of this node R we have the noun, and the noun itself is divided into an adjective and a noun, right? So fast computers, and on the right hand side we have also more energy efficient, right? So also is an adverb, more is an adverb, and energy efficient is yet another adjective. All right. So we learn these kind of rules in English language grammar, and we kind of use these rules to identify and parse sentences. It is not very different in computers or programming languages. So here is a sentence, a programming sentence or a statement in a language like C. If foo is less than equal to 2, then bar, else x equals 5. Now, after we have identified the tokens, which we have done in the last step, we would like to understand the structure of the sentence. And in this case, the structure looks something like this. The top level here is the if then else construct, right? So the whole statement is basically an if then else statement, right? And the other things are kind of filling in parts of the statement. So the root node of the statement is if then else in the diagram. And this root node has three different parts to it. The first part is the condition, which goes with if. The second part is the statement that goes with then. And the third part is the statement that goes with the else clause. Okay. So now the condition itself is supposed to be an expression that evaluates to a Boolean value. In this case, that is represented by this subtree foo is less than equal to 2, right? So less than equal to 2 is the operator that generates the Boolean value, and it compares two parts of two expressions, the left part and the right part, and in this case both those left and right expressions happen to be leaf nodes. One of them is an identifier and the other is a constant. Similarly, in the then clause, the next level is a function call, and the function call basically has its own operands. In this case, it only has one operand, which is the name of the function. If the function call was making a call using more than 0 operands, then it would have had maybe 1 or 2. So if the function call had one argument, then the function call operator would have had 2 children, right, and so on. Similarly, the else clause involves a statement, and in this case it's an assignment statement, so the root node is an assignment operator, equals, and the left and right nodes represent what is assigned to what. Alright, so this process of converting this linear stream of tokens into a structured tree or diagram that represents the structure of the program is the process of parsing. Alright. The third step of compilation is semantic analysis, and here we are more interested in understanding the meaning of the sentence. So we've already kind of identified the structure of the sentence, and but now we want to understand the meaning of the sentence. Now, what is the meaning of a sentence? I mean, that's a very fuzzy statement. Actually, the meaning of a sentence would mean what is the program actually doing, and that is a very difficult problem. And theoretically speaking, it's an undecidable problem. And similar to saying whether this program is equivalent to something else. So can the compiler look at a program and say that, oh, it is actually going to produce a sorted output, or it is the quicksort function or something like that. Well, something like that is pretty difficult to do. Instead, what semantic analysis does is it just does some basic checking, right? For example, it would check inconsistencies like a variable is defined before it is used, or that things are not used outside the scope, or it's going to provide bindings for things within the scope, or it's going to check whether things are used consistently with the types of those objects. So these are called catch inconsistencies, and this kind of catching inconsistencies is faster than actually doing a full understanding of what is the meaning of the sentence, which compilers would not do not tend to do. So there's no effort by the compiler to understand the actual meaning, but at least there are some inconsistency checks that can be done by the compiler. And this part is called the semantic analysis. So here's an example of semantic analysis for the natural language. Once again, taking an analogy from the natural language. So let's say there's a sentence called, the compiler generates an executable and it prints nothing when it runs. Now here, when I look at it, there are two parts of it. So first of all, this sentence looks like a linear sequence of characters or string of characters, which after the lexical analysis pass is going to give us a linear stream of tokens, which after the parsing pass is going to give us a sentence tree structure, right? So for example, it's going to say, maybe the top node of the sentence structure is going to be the AND node, which is the conjunctive operator, and the left part of it is saying something, and the right part of it is saying something, and so on, right? So we're not going to look at the parsing part. But now once the parsing has been done, we want to understand whether, we want to check whether there's some things which are consistent here. So for example, here we say, it prints nothing when it runs. What is it? Is it the compiler or is it the executable? Also, there are two its. Are the two its referring to the same entity? Maybe both of them are referring to the compiler, or are they referring to different entities? For example, the first it is referring to the executable, and maybe the second it is referring to the compiler. So all these things are basically under the purview of the semantic analysis. Now in this case, actually, it is a bit ambiguous, frankly, what does it refer to? And this can be called an ambiguity in the natural language of English. And similar ambiguities may be present in a programming language, but because the programming language is more technical, we should always have rules to resolve ambiguities, and in the end there should not be any ambiguities. All right. So, okay. So this is similar. I mean, this example where I'm saying, what does it refer to? This example is kind of similar to scoping rules in programming language. So consider an object-oriented language where, let's say, there's a class foo, and within the class foo, there's another class bar encapsulated within class foo. And then I use this keyword called this. Now assume this is something like C++, for example. So now what does this mean? Does this mean bar or does this mean foo? Now, C++ would have very clear rules that this would basically bind to the closest context in which it is being defined. So in this case, this would mean bar, right? So this kind of analysis and checks is basically being done by the semantic analysis phase. Notice that apart from doing checking, it is also basically identifying the meaning. So for example, it's identifying the meaning of this. In this case, this refers to an object of type bar. Okay. The other part is checking, right? So here is another example of an activity that a semantic analysis phase is supposed to do. It's supposed to check types. So the compiler generates an executable and it prints nothing when they runs. Now in English, this is an illegal sentence and the parser won't be able to catch it because it's still the same structure. But notice that it is a singular, it is singular, whereas print should have, and so print should have had an S here, right? And that's missing, and that looks like a type error, all right? So print can't be used with it. And similarly, when they runs, So they and runs don't go well together. And what does it mean? Like it print when nothing when they runs. So sometimes we're talking about it and sometimes we're talking about they. Now, is it actually consistent? Does it make sense? This is what a semantic analysis phase is supposed to check. Now, in a programming language, coming back to the programming language world, let's say I have char star p, and then I say q equals p multiplied by 5. Now, this is a type error because a pointer cannot be multiplied with anything else, right? And so this is similar to a type error, and a type error like this is also identified during the semantic analysis phase. Now, is it a coincidence that there is so much similarity between a natural language processor and a programming language processor, a compiler? Well, I don't think so. In fact, programming languages are sort of in many ways modeled on natural languages because the whole point of doing a programming language is to make it easy for humans, and humans are already good at doing natural languages. All right. The next phase of a compiler is optimization, where a compiler modifies the program without changing the meaning. Right? So that's important. Without changing the meaning. Okay? Because if it changes the meaning, that would be an incorrect compilation. And why does it modify the program? Well, there could be, either because the modified program runs faster, or it uses less memory, or it reduces the power consumption of the program, or reduces the network messages, reduces disk access, and so on. So there could be, depending on the environment, different metrics, and the compiler may want to modify the program to optimize for that particular metric. Now, this is a major part of a compiler, as we discussed last time, and probably this doesn't have too much of a counterpart in natural language processing as well. You can think of optimization as editing, except that optimization is much more heavyweight process than what editing is for a natural language in the context of natural languages. All right. Also, it is important to know that optimization needs to be very careful about preserving meanings, and preserving meanings typically requires careful semantic modeling. So consider this expression 2 into I by 2. Can I replace this expression by I in a language like C, assuming I was an integer, a C integer? Well, the answer is actually no. All right. And why is it a no? Because imagine if I was a quantity that was larger than half of the maximum value that can be stored in an C integer, in which case 2 into I would overflow, and depending on the semantics, it may happen that the topmost bit is lost because of 2 into I, and so the value of, in that case, of 2 into I by 2 would be different from the original value of I. Right? It would probably be something that has the topmost bit removed, turned to 0. Okay, so you can't do these kind of things, and basically pointing out that optimization requires precise semantic modeling. Here's another example. Let's say I have a variable of type float, and let's say I'm initializing y, which is a float variable, in different ways, and then I have this expression called z equals y is into 0. Now, because of the peculiarities of a floating point arithmetic, it is not okay to convert y into 0 to 0, because y into 0 could be something other than 0. All right, and also there is the notion of negative and positive 0 in floating points, so one needs to be careful about making these transformations. In fact, something like this is illegal. All right, here's another example. Let's say I have a loop. So let's say in this case I have, first of all, in this example, I'm considering the C language. And let's say in the C language, I have a variable I of type unsigned. And then I have this loop for I equals 0, I is less than n plus 1, I plus plus, and then I do something. Is it okay to convert I is less than n plus 1 to I is less than equal to n? All right. In fact, it turns out that this is not okay in this program. All right. This is not okay in this program. So this is not okay. Why? Well, because it is possible that n was maybe the largest possible unsigned integer, in which case n plus 1 would wrap around and overflow, and in which case this loop should never execute, right? Because it will become I equals 0 and I is less than wrapped around value, and typically with the largest value, when it wraps around, an unsigned value will wrap around to, let's say, 0, and so it would become I is equal to 0, I is less than 0, and so this becomes false and the loop will never enter. On the other hand, the program on the right, if n was the largest unsigned value, would execute for forever actually, because it's going to be always less than equal to that, because I is actually an unsigned integer, and because it's an unsigned integer, it will always be less than equal to the largest integer ever, right? So this transformation is wrong, all right? So this transformation is wrong. But it turns out that if I replace the type unsigned with the signed integer, right? So if I instead have a signed integer, so in C, an int is supposed to be a signed integer. If you do this, then this becomes okay, all right? This is okay. Now, why is this okay and why is the previous transformation not okay? How does it make a difference whether I was an unsigned or an signed integer? Now, for this, we need to understand the deep semantics of the C language that I'm not going through in this lecture, but we'll probably get a chance to discuss this later in the course. All right, and then the final phase of a compiler is code generation or translation. Now, this is the instruction set architecture aware phase. So you need to know about the ISA. And then you basically translate patterns of instructions in the optimized program to the low-level instructions that the machine can actually implement. And in fact, this is not usually the only phase that is ISA aware. Some optimization phases also need to be ISA aware, so that we basically come to this stage where the best possible instructions are chosen to be executed on the hardware. And so code generation phase usually also includes optimization, and optimizers also usually need to be ISA aware. So these things actually, while I'm kind of showing them as separate phases, they usually depend on each other for generation of good quality code. All right, here's a rough division of compiler complexity. So if I look at a modern compiler like GCC or LLVM, how much of the complexity is due to which part of the compiler? Well, it turns out that things like lexing and parsing are relatively well understood, and they're relatively pretty simple. So for example, consider GCC or LLVM, which are into the millions of lines of code complexity. A lexer and a parser would only be less than maybe 100 or 200,000 lines of code. Semantic analysis is also relatively well understood. It may be slightly more complicated than parsing, but a small fraction of the overall complexity. Optimization and code generation are by far the biggest contributors to a compiler complexity, and of which optimization takes the major share.